Hello everyone. Um, we are the Titan team, and I want to present to you our project on CDS scan, detecting seeds in CDS scan images from a dataset provided by Alpha Tau. I am Milad Rajwari, and I will be the representative of the group. Um, so the task is to detect seeds in CDS scan images from the dataset. So uh, we have some slices of the tissue that is scanned by the CT scan, and we need to find the seeds that are planted by alpha tau in to the tissue. Um, and in order to give you a good insight about what the problem actually is, you can see the CT scan images here in the left, and this is the mask that in which the seeds are portrayed with white pixels. And as you can see, it's actually pretty hard to detect where the seeds are planted just from the image. So it's not an easy task. Our approach is to break down this complex problem, to some subproblems because of the limited data and also limited computational resources that we had access to. The first part is to perform a semantic segmentation on the 3D input that we have, and one of the dimensions is time, the time of scanning with the CT scan, and we want to perform a semantic segmentation to know exactly which pixels are from seeds and which are just background or normal tissue. And after we have the semantic segmentation, we can use that to detect the number of seeds, and you can use that with clustering on the cloud points of the seeds, or we can do that with a neural net that you feed it this 3D image input, and it spits out back the number of seeds. And when you have a number of seeds, because of the form of these seeds that we know is very close to Gaussian mixture. I mean, each seed can be modeled perfectly by a 3D Gaussian variable, random variable. We can just model all of the seeds in this 3D space with a mixture of Gaussians. And after we cluster this with a Gaussian mixture, we can extract the position of the seeds and also the orientation just from the parameters of the Gaussian mixture. So the position will be the means, and the orientation can be extracted from the covariance matrix. So for the semantic segmentation part, we use a famous architecture called UNet. And actually, we found out that if we use a pre-trained UNet that is pre-trained on MRI images, it would perform much better. If we just want to train it on the limited data we have, also because we have limited computational resources, and we're treating the depths as color channel in our covenant. So because the model is actually pre-trained assuming that the channels are color channels, but we just use it as depths. So what we do is we split this 3D image to some 3D slices. So we concatenate the current slide, the current slice of the CT scan with two neighboring slices and feed it to a neural network that should produce the mask for that layer that is in between. So we generate the semantic segmentation mask one by one. So we kind of swipe through the time and we generate the semantic map, and we found out that it actually performs pretty well. And after we have that, we can find the number of seeds in this 3D volume, as I have said, using convolutional 3D neural networks. But so in the plot, you can see a conv 3D, and this seems fancy and it should work, but we couldn't make it work actually. But a very simple model called a Bayesian Gaussian mixture model could do pretty well. That it just what it does is it somehow doesn't use some of its components. So we just ignore those components and count how many components are being used, and we use it as seeds. And well, it's not perfect, but it kind of worked. But it was surprisingly the worst performing component, and actually the most time consuming. We couldn't make it work very well, but it works well, to some extent well. So what we do after we find the seeds is we feed a Gaussian mixture model with that number of components to the data, and then we treat each one of these Gaussians as one of our seeds. So uh, we know that because these seeds are actually like a rod, like a small rod, they can be perfectly modeled by a Gaussian mixture. And after that, the position of the seed can be extracted just by the mean of this Gaussian distribution, and the orientation can be extracted from the covariance matrix by finding the eigenvector with the highest eigenvalue, because it shows the direction of the Gaussian distribution and it's actually the direction of the seed in the tissue. And here I want to show you some results of our method. So these are some, so the blue color is the ground truths. So these are real seeds, the real seeds in the data. And the red dots actually we are plotting them with alpha less than 1 to, because we can see them. The red dots are what we have predicted. So our prediction is not perfect, but it's kind of good. As you can see, we predicted a dot here that is not a seed. Or for example, here there are some ground truth seeds that we have not covered, the model have not covered. But in these two images, pretty much the coverage is 100% and is very clean with no false negative, maybe except this spot. And these are the seeds or the semantic map we have produced for the test data. So we don't have the ground truths here, and these are what the model have predicted. As you can see, some of them are very clean, like this one or this one, kind of this one, and some of them are noisy. So the model is kind of performing good, but I think it can use more time being invested into it to become better. So I think for future improvement, we can use different architectures to do the semantic segmentation. We can use a comp3D or a unit 3D. Maybe the current implementation is not the best one. Also, because the model is pre-trained on MRI images, it's not, I think, good either. Maybe training from scratch with more computational resources would be good. The seed counting problem, maybe if it is being treated as a classification problem, it would be better. And also, I think it should be solvable. We just didn't have the time to search through good architectures for that problem. And also, if we use a mask or CNN or an end-to-end model, I think it would do better. But certainly, it needs lots of time and also computation. So that was our presentation, and thank you for your attention. Yeah, goodbye.